SMJP 1022 Materials Science Chapter 5 Dislocation and Metal Strengthening Mechanism. In this chapter, we will look at the deformation, mechanism of metal strengthening, grain size, and finally, solid solution. In this video, we will cover part B, which is strengthening of metal. In order to strengthen the metal, we will need to have information of yield strength, ductility, and toughness of both crystalline and amorphous materials. These help the engineer to modify the metal in order for the application. In order to modify, the engineer have to understand strengthening of metal, especially in its mechanism. It will give engineer the ability to tailor the mechanical properties of materials. And finally, to suit a variety of different applications. In the strengthening of metals, we have three kind of thing we need to look at. The first one is basic concept of strengthening of metal, which is plastic deformation in metals is caused by dislocation movement or dislocation motion. And what is the strengthening strategy? The strategy is to restrict or hinder dislocation motion. And finally, for the strengthening techniques, there are 4 items can be done. The first one is grain size reduction. The second one is solid solution alloying or solid solution hardening. The third one is strain hardening, and the final is a precipitation hardening. For the basic concept of plastic deformation in metals is caused by dislocation motion, is very important to understand relation between dislocation motion and metal mechanical behavior. Dislocation motion is the ability of metal to be deformed depend on ability of dislocation to move. Restriction dislocation motion makes the material stronger. The more unconstrained the dislocation motion, the easier a metal may deform. For the strengthening strategy, by reducing mobility of dislocation, deformation become difficult. Greater mechanical force required for deformation, actually. And we can see a mechanical strength is enhanced, and as a result, restricting or hindering dislocation motion will make a material harder and stronger. This is the way of strengthening of metal. four ways we can see in order to strengthen the metals. The first is grain size reduction. The second one is solid solution hardening. Next is strain hardening. And finally, we have a precipitation hardening. For the mechanism of strengthening, we will see is a grain size reduction, solid solution alloying, strain hardening, and finally precipitation hardening. Number one is grain size reduction. Grain size reduction influence mechanical properties. Adjacent grain have different orientation and common grain boundaries, which is you can see from this diagram. We have adjacent grains beside the grain boundary and have a different orientation or different arrangement within the red atom and green atom. During plastic deformation, dislocation motion will try to go through common boundary, which is grain A will move to grain B. You can see dislocation motion from the slip planes move to the right and reach at the grain boundary here. But grain boundary will act as a barrier. It will block along this line. The two grains are of different orientation. Dislocation have to change direction. Becomes more difficult when misorientation increase, which is misorientation is increased whereby the angle is produced very high angle. The atomic disorder within boundaries region, discontinuity of slip planes from one grain to another. Grain size can be controlled by rate of solidification, whether it's slow or fast solidification, plastic deformation, heat treatment. Next subchapter, we will look at the heat treatment, consists of several techniques. Fine grains materials has greater total grains boundary surface area than coarse grain material. So if compared to the big or coarse grains, the fine actually has greater total grain boundary surface area. It will prevent more dislocation motion. So for fine grains material, it will prevent more dislocation motion, and finally it will produce a harder and stronger material. This is due to the yield strength increase. If you look at the stress strain curve, it will increase a little bit more. So, and finally, it will make a material harder and stronger. As more and more dislocation pile up at the grain boundaries, a larger stress is required to move them, and the onset of plasticity is delayed. Hence, the yield strength increase by this mechanism. So, for the grain size reduction, the fine grain is very important to produce a harder and stronger material. Relationship between grain size and yield strength sigma y is the by using Hall patch equation, which given as this equation, which is depend on the grain diameter or grain size, friction stress or resistance to dislocation motion, and finally hardening contribution from the grain boundary. Okay, in order to block dislocation motion, twin boundary or twin plane is very good. It can block slip process efficiently. By looking at this diagram, this is, we call it a twin boundary, whereby we have a symmetry of grain 1 and grain 2. So it can prevent dislocation motion. Angle grain boundary can be seen in this figure. We have three orientation of grain and produce a wide angle of misalignment, can be seen in this line, and it also produce a very low angle of misalignment, can be seen in this line. Okay. At the same time, it will produce a high angle grain boundary in this line, and also we call it a small angle of grain boundary in this line. Grain boundary angle grain boundary can be seen in this schematic diagram. We can see a three set of grains, which is the orientation is different. If you look at this grain, angle grain boundaries, we can see from this diagram the three set of grains, which is the different orientation. You can see this grain is orientation is in this direction, whereas the second grain is this atomic arrangement is in this direction, and the third is atomic arrangement is in this direction. It will produce a high angle of misalignment if you compare to this angle through this line, and it will produce a high angle grains boundary. And the second one, we have a small angle of misalignment can be produced with two different orientation of grains, and it will produce a small angle grain boundaries. High angle basically difficult for this location to go through, and for the small angle, it we call it slightly misaligned, and it is not effective in stopping dislocation motion. And the second way to strengthen the metals by using a solid solution hardening. Basically, pure metal is soft and weak. So in order to make it harden, okay, we have to combine with one or more other elements, and it will become a alloy. If you look at the stress strain curve for the pure metals here, if we put foreign metal or impurities to the pure metals, it will become a very strong and hard alloy. And if we do some stress strain testing, it will produce a very high graph, indicates yield stress or yield strength increase. Before we go through, we need to understand a little bit or information related to alloy. Alloy basically a combination of metals or metals combination with one or more other elements. The other element basically we will call it impurities. When the alloy cools and solidifies or crystallize, mechanical properties change. For example, the combination of metal element gold and copper produce red gold. Silver with copper will produce sterling silver. Aluminium with copper will produce aluminium alloy. Iron combined with carbon, a small amount of carbon will produce steel. The combination of aluminium with copper or maybe magnesium, manganese, silicon or tin or zinc will produce aluminium alloy. Aluminium basically is very soft and malleable, and if we combine two impurities, it will make a aluminium alloy which is much harder and stronger. Combination of iron with carbon will produce steel. It will result a very high strength and toughness, which is much higher than pure iron, and its ability to greatly altered by heat treatment. Steel is the one of the most common alloys in modern use. Alloying a metal with impurities atom, or sometimes they call it solid atom in different way, either by substitutional or interstitial solid solution. This substitutional or interstitial basically we learned in previous chapter. So I don't want to explain more about this. Impurities atom generate stress by distorting the lattice or produce. lattice strain on host atom. When the impurity get inside the atoms, host atom, it will produce a lattice strains basically. Impurities basically interact with dislocation strain field that can produce a barrier to dislocation motion, or it will stop, it will block the dislocation motion, which increase yield stress or the materials. Impurities tend to diffuse and segregate around dislocation cores to find atomic site that suit their ready. This reduced the overall of strain energy and hindered dislocation motion. Basically, we will explain in three ways. Basically, the keyword is impurities atoms, and then it will produce lattice strains at host atoms, and finally, it will act as a block for the dislocation motion. The presence of impurities atom impart compressive or tensile strength to the lattice depending on impurities atom size. Okay. If a smaller impurities atom, basically it will tend to concentrate at position adjacent to dislocation and above slip planes here above. Okay. So it will produce a tensile lattice strain. Meanwhile, for the larger impurities atom, it will tend to concentrate at opposite to dislocation and below slip plane at this area. Okay, and it will act as a compressive lattice strains. Okay, thank you very much. Bye bye.